Okay. Okay. I guess it's good now. So. Good morning, everybody. We're continuing from chapter 2. We started Kirchhoff's laws. We were doing Kirchhoff's current law. And we discussed this analogy with current flowing through a wire or through an element, the similarity between that and water flowing through a pipe. And if you have a number of branches coming together at a node, then you have to sum all the currents going into that node. That has to be equal to the sum of all the currents leaving that node. So we did that last time. KCL also applies to a closed boundary, not just at a node. So for example, if you look at this drawing right now, you have all those different branches, the red ones, and if you take any node, any individual node here, you can write a KCL at each one of those nodes. So you would come at any node and you would say, oh, the node has to be equal to the sum of the currents leaving that same node. But you can also apply that at around, like, across a closed boundary. When you have a closed boundary and you find the boundary in green right here, you can also look at that boundary, ignore what's inside the boundary, and look at it from the outside. Anything that is crossing the boundary, entering into it, the sum of those currents has to be equal to the currents going out of the boundary. So I'm going to do that particular one right here. If you have currents like that, okay, I'm going to give them some names. Call this I1, I2, I3, I4, I5, I6, I7, and I8. So KCL, say at node A, I would say the sum of the currents entering that node, which are, actually it's only I2 entering, that's equal to the sum of all the currents leaving. That's going to be equal to I5 plus I6 plus I7. That's how we would do KCL at a node. But if I want to do KCL around the closed boundary, and you have a boundary like this, and I would say the sum of the currents entering the boundary has to be equal to the sum of the currents leaving the boundary. So KCL at boundary, you would have I1 is entering plus I4. These two are the currents entering the boundary. That's equal to I6 plus I7 plus I8. Okay? So this is how you would apply KCL around the closed boundary. Now, simple application. We're going to see some simple applications of KCL, and it's going to give us some insight into some other elements as well. So for example, you have that drawing where you have those three current sources. You see that? I1, I2, and I3. I have three current sources here. and I have a current called IT, I total. Now, I total is the current that is going to be seen by that blue element. That blue element is probably what we tend to call a load. Doesn't really matter what it is. But if you want to know what is IT, the total current here, then what would you say? If you look at this point up there, that's one node, and you can write the KCL, then say IT is equal to, that's current going out, that's I1 plus I3 minus I2. Okay? So I have I1, I2, I3. I want to know how much is this current, IT. So I'm going to write a KCL at this node. It's all one node, remember? I call it node A. So KCL at node A. I have the currents flowing in. I have I1 plus I3 equals the currents flowing out, which is IT plus I2, right? I want to know how much IT is. IT is equal to I1 minus I2 plus I3. Now, what we're trying to do here, I'm going to take I1 and I2 and I3 all together. See, like I drew this this green line around them, and I want to replace all of that by a single current source. That's the same current that I had in the first place. Okay, so I'm going to have a current source here I. If I have current here IT, how much should this current I be? This current I has to be equal to the current IT, right? And IT have the exact same effect by replacing them with one current source. Same direction. So this current I is it will still work. Okay, we're going now to look at Kirchhoff. So that's called a closed path or a loop. A circuit here where you have 2 volts, 2 resistors, and an extra element. We don't really know what it is. And I'm going plus minus plus minus V5. Now, that loop. Okay, it's a close here. And I'm going to go around that, okay, from any point, doesn't matter. The idea is you go around a loop, you start from a point, you have to end up at the same point. Some voltages, see, like I'm going from here to there, I'm going to start from here. I'm going up the first element, right? I'm moving like this. I'm going from a negative to a positive, okay? And then as I move from here to here, going from a positive to a negative. Then I'm moving like that, and from a negative to a positive. And that's the last stretch, going from a positive to a negative, okay? So as you're going, you're going to find that some voltages are going to be across that element that you're passing through. Those voltages are going to be like plus minus, and sometimes they're going to be minus plus. So you have to add them up algebraically. What it means here, you have to, for example, if I go from minus to plus, and I'm going to write V1, then if I go from plus to minus, I have to change the sign, right? So I'm going to say minus V2, plus to minus is still the direction of minus V2, minus to plus, that becomes positive again, plus to minus, minus V5. That's equal to 0. I'm going to rearrange that. So I have V1 plus V4 equals V2, so that's 3, V2 plus V3 plus V5, right? And let's walk again and let's see what we're getting here. Remember the definition that we had, if it was last lecture or the one before, about voltage rises and voltage drops. What is a voltage rise and what is a voltage drop? If I'm going from this point to this voltage level to a higher voltage level, this is called a voltage rise. So V1 is a voltage rise. What about V4? I'm going in this direction, from a negative to a positive. So I'm going from a value of voltage which is lower to a value of voltage that is higher. So again, this is a voltage rise. Let's look at V2. I'm flowing. This is the direction of flow. That's how I was walking around my loop. From here to there, that's from a higher to a lower. So that's called a voltage drop. So this is a drop. Same thing for V3, from the plus to the minus. That's another drop. And eventually from V5, you look at the end here, I'm walking in the direction of a voltage drop because I'm going from a node which has a higher voltage to a node which has a lower voltage. So it's also a drop. So this basically is what KVL boils down to. It says, as you're going around a loop, you choose the point where you're starting, you have to end at that same point, and you go in whichever direction you like. It can be clockwise or anti-clockwise, doesn't matter, it's always going to work out right. What you're trying to write for a proper KVL is the sum of the voltages that are, the sum of voltage rises has to be equal to the sum of the voltage drops. Okay? That's basically what KVL is trying to tell us. That sometimes people get confused with KVL. KCL you have to solve by yourself. You have to take the problem sets and you have to attempt to solve them by yourself. Please, if you just think that you learn the concepts and you wait for somebody else to show you the solution, you're practicing a lot of KVLs, and this is a basic principle. Here we're going to apply KVL. So we have a circuit. Regardless of what element exists here, we discover that if you look at those voltage sources, V1, V2, and V3, if you look at all of these together, now the element that's in here is going to feel some kind of a voltage across these two terminals from here to here. That's what this element sees. Okay. Now, how much is this voltage in terms of V1, V2, and V3? We're going to call that VAB, given that this is node A and this is node B. So we want to know how much is VAB. So the way to do that is going to be through KVL. I'm going to start from this node, and I'm going to go all around. Now from here to here, this is that rise of a value VAB. That's rise. Okay, let's go from here to here now. As you're going down here now, until this node, you went from a plus to a minus, so this is a drop of V1. So I'm going to put V1 on this side, that's the side of the drops. What about this one? Right? As I'm going in this direction, I'm going then from a plus to a minus, so that's again a drop of V2. And then as I'm going from here to here, I'm going from minus to plus, from lower to higher. So this is a rise again. So I have here V3. Okay? So the sum of voltage rises is equal to the sum of voltage drops. So how much is VAB now? V1 plus V2 minus V3. Which means if you replace this source by another source equal to V1 plus V2 minus V3, it's going to have the exact same effects between the two nodes A and B as you had with the three sources. And often in circuits, we like to simplify things. So if I have 2, 3, Okay. How am I going to find those two voltages, V1 and V2? I'm going to represent, I'm going to show that, assume it looks like this. Okay, and I'm going to write the first equation by going around that and writing KVL. Start from here. So I'm going like that. Is that a rise or a drop? Starting from here, and I'm going in this direction. That's a rise, okay? 20 volt rise. And then, what about this one? Is this a rise or a drop? That's a drop. So I'm going to go on the other side. And what about this one? I'm going like that. Is that a rise or a drop? That's a rise again. So plus V2, okay? So by rearranging that, I have V1 minus V2 equals 20, right? That's one equation there. Okay. What other equations do I have? Let's see. Now these are resistors, right? What do we know about resistors? Ohm's law. Okay? Alright. So I'm going to say I have a current here. I'm going to call that I1. And what can I write here in terms of Ohm's law? What's the relation between the voltage, the current, and the value of the resistance? What can I say? V1 equals 2 times I1. Okay? So V1 equals 2 I1. Alright? Screen froze. Screen froze. Still frozen? What should I do? Okay. Is it back on? Yeah. Okay. Okay. So I have Ohm's law tells me that V1 equals 2I1. That's another equation I have. And I need to write another equation from here. Look at this one. Now this one is going to be a little bit tricky because we know that the current inside the resistor always has to, to write a proper Ohm's law, current should look like this. I1 should flow in this direction because it has to flow inside the resistor from the high to the lowest. That's what Ohm's law tells us. 3I, sorry, that's I2. So V2 equals 3I2. Okay? Finally, still frozen?
Frozen again. For some time.
I'm going to finish this quickly now. Anyway, is it working? Is it back on?
No.
I disconnected and connected it again. It's better now?
Shows this, but I don't know if it's.
It shows this, so well, let's see. Anyway, I'm going to use these three equations together, but I'm still missing one more. I'm going to write a KCL here. Look at that. KCL says that the sum of the currents flowing into the node is equal to the sum of the currents flowing out of the node. So what do I have? I1 is flowing in and I2 is flowing in, so I1 plus I2 equals, where's the current flowing out? I1 plus I2. Is there a third branch? That's equal to 0. Yeah.
This is not.
It's still not.
PowerPoint is okay.
PowerPoint is okay. So now I have that third equation, I1 plus I2 equals 0, and I'm going to use all of these equations together, and I'm going to put them here. So I have, instead of V1, I have 2I1 minus 3I2 equals 20. And from here I have I2 equals negative I1. Okay, so 2I1, instead of minus 3I2, I have plus 3I1 equals 20. So that's 5I1 equals 20. I1 equals 4 amps. Okay, so did you see that? I'm using KCL and KVL and Ohm's law together, and I wrote a bunch of equations, and I solved those equations. And I found that I1 equals 4 amps. Now, how much is V1, which is like the purpose of this whole thing? V1 equals 2I1, that's equal to 8 volts. V2 equals 3I2, that's equal to negative 3I1. That's equal minus 12 volts. Okay. Yes.
I'm just curious, how can voltage rise across the resistance?
You can't.
Yeah.
So that's why, look what happened. We end up having V2 equal to negative 12 volts.
Okay.
So, once you, look, if you put it clearly from the start and you're following the rules, it's going to end up fine at the end. Let me show you what we ended up having. We ended up having the following. I'm going to draw this circuit here again. Okay, 3 ohm, 2 ohm. And what do I have? I have V1 is 8 volts, right? V2, look at the polarity here. It was minus plus with a negative 12 volts. Effectively, I have something that looks like this, right?
If you just drew it that way initially.
Yeah, exactly. If you had drawn it initially, it would have kind of been more intuitive. And then look at the current. You have this current, which is 4 amps, and this current I2 is negative 4, which means that you have this current, which is 4 amps. And this is the real picture now.
So would you be able to denote that? Like, does voltage, it's sort of arbitrary, right? You can
Exactly.
switch it if you wanted to.
Now, if this is a problem that's from the textbook and says, I want to know how much is V1 with this given polarity and how much is V2 with that particular polarity, okay? So given those polarities, those assumed polarities, then what we did was write, and we end up having that V1 is 8 volts and V2 according to this polarity is negative 12. Okay? But if you're working on a problem yourself and you're putting the polarity, it just makes a lot more sense to kind of assume plus minus V1 and then plus minus V2 from the start. Okay? Make sense? Okay. Example 2.6. Now this is again another problem with KVL, KCL, and Ohm's law. Chris, I'm still not working, eh?
Jordan is not here. I texted him, he'll be here in 10 minutes.
Okay.
Maybe in the meantime, you can use the PowerPoint site.
Very, very tricky. Let me try.
Possible.
Let's see. If I'm using the PowerPoint pen. Now, let's see again. What here? I have this direction. I'm going to say I have a voltage rise of 12, right? And then, here, they're not giving me any polarity. So I am going to assume the polarity. I'm going to put it like that. Plus, minus. I'm going to call that D1. So here, this is a drop, right? As I'm going in this direction now, I'm getting a voltage drop. So I'm going to put the drop on this side. And then I'm going to proceed here. What do I have? A rise or a drop? What do I have here? It's a drop of how much? 2 V naught. So I'm going to put it here. Plus 2 V naught. Okay. From here, what do I have? Like that. Rise or drop? Here. That's a rise. Okay? Going from the minus sign to the plus sign. So here you have a rise of 4. It's going to come here on this side. And then finally, I'm going here. That's a rise again from minus to plus. Okay? So that's going to come here. Plus V naught. Okay, so now I have an equation which has V1 and V naught. Okay? So what do I have? I have here 12 plus 4, that's 16. Equals V1 plus, I have 2 V naught and then I have 1 V naught that is going to go on the other side. So I end up with V naught, right? Okay. So this is the first equation. Now we need to write a few other equations. I'm going to write a here you're going to write Ohm's law here. Okay, you can also write Ohm's law here. You're going to combine the different V1 equals, equals 4I. And then from the bottom here, I have, do you see this current I? Now this current I that's flowing in here is going to flow. Remember when we were talking about elements in series, that how the same current keeps flowing from one element to the other as long as they're in series? So this same current I is the same current I that I have here. It's the same current I that I have here. And it's the same current I that I have here. That's current I. So I can write another KVL equation down there. But now be careful. The current I and the voltage V0 that are put here, they are not according to the passive sign convention. And that's important for Ohm's law. Ohm's law always says that the current in your resistor has to flow from the higher voltage to the lower voltage. So I have to be careful, and I have to say, oh, okay, if that's the case, then I have, it's like I have a voltage like that here, plus here and minus here, and I have negative V0. And I have the plus and minus in the same direction of the drop for the current. Now I can write an Ohm's law here. I'm going to say that minus V0 equals 6I. Okay? Now look at these three equations. If you substitute, you remove V1 from the first line, you're going to have 4I. And you move V0 from the second line, you get negative 6I. Then you're going to solve, you're going to find the value of I. All right? And then once you have the value of I, you put it back in here, you get the value of V0. So just solving these now is going to give you the value of V0 and I that you're looking for. So again, the whole idea is you have to know how to apply KCL, KVL, and Ohm's law. Any questions in this problem? Okay. Let's take one more. Jason, this is still not working?
No. Still.
No?
Still.
Let me try again. Because working like that is a pain. Do you have anything? I restarted it.
Then you can do. No.
No? Okay. Somebody was suggesting that people on the other end can look up the solutions and follow the solutions with us because they're in the book. So I'm going to try as much as I can, like some here and some on the PowerPoint, but I can't like keep going, it's too slow. So let's look at this one. I have a current of 0.5 I0. Okay, 3 amps. Node A, 4 ohm, plus or minus V0. Okay, so what can I do? I'm going to, well, first let's see. Can I write any KVL equations here? Now that's an important question. If you look at that, KVL says you're going around the loop, right? And you are writing equations based on voltage rise and voltage drops. Now, if somebody wanted to write a KVL here, and I'm going back to the PowerPoint. If you want to start at this point, like here. So What is that? This element is a current source, right? How much voltage do I have across the current source? Do I have a rise or a drop? I don't know. And that's the whole point. By definition, a current source tells me how much current is flowing through the branch, but doesn't tell me how much voltage is there. So I cannot start by writing a KVL if I have a current source in the branch. I cannot do that. And now if I go down here, yeah, I have a voltage drop here. I can do that. But I can, if I want to go through the other loop, again, I have this problem. I don't know the voltage, so I cannot go there. So you're going to find if you have current sources in the branches, you cannot write KVLs. And I have to write KCL. So I'm going to do that. I'm going to write a KCL at this node here. So if I go here and I write KCL, sum of the currents flowing in is equal to the sum of the currents flowing out. I have two currents flowing in. I have 0.5 I naught plus 3 amps. Both of these are going into my node. That's equal to one current flowing out, which is I naught, which is flowing downwards through that middle branch. So I have this equation, 0.5 I naught plus 3 amps equals I naught. Okay? And from here, you have I naught minus 0.5 I naught, that's 0.5 I naught equals 3 amps, means I naught equals 6 amps. Okay? So that's the first part of the solution. I naught is 6 amps. The second part, we want to find V naught. How can I find V naught? I have I naught. What should I do? I don't need these, right? So I have I naught, it's 6 amps. How about V naught? How can I get V naught now? Yes. Ohm's law, what does it say? V equals IR. V naught equals 4 I naught. Is the current and the voltage like aligned? Are they positioned correctly on your resistor? Yes, they are. So V naught is equal to 4 I naught. Okay, and this is how you get the voltage V naught. Any questions? Okay, here's one more example. Find currents and voltages in the circuit shown. So again, this problem, this example, again, because technology is not like helping us too much. For those who cannot see the webcam, this is in the book, so you can see how it goes in the book. But basically, all you need to do is just use what you know. You're going to write KVL, KCL, and Ohm's law. Now, in this particular problem, we're going to write one KCL, right here at node A. And can somebody tell me what would that KCL look like? Sum of the currents flowing in equals the sum of the currents flowing out. Yes?
It would be I1 equals I3 plus I2.
I1, yes, exactly. So you're going to have this equation I1 equals I2 plus I3, right? That's KCL at node A. Okay, so we have one equation now. I want to write other equations. Can I do KVL here? Okay? Look at that. If you look at that, the left inner loop, can you go around it and write a KVL for me? I want somebody to tell me how it would look like. There's a voltage source, and yes, you can write KVL with voltage sources. So if you start at the corner in the bottom there, and you go up, yes?
30
So 30, that's a voltage rise, okay? And then?
minus V1 And minus V2 is equal to 0.
Okay, so this is a voltage rise 30, and then you go through V1, that's going to be a voltage drop, and then through V2, that's another voltage drop. So you have this equation, okay, that's KVL. You're going to say 30 equals V1 plus V2, right? That's the second equation. I need one more equation. Now, the third equation, you can go around the second loop, the second inner loop, or you can go around the outer loop. The number of independent KVL equations that you can write is equal to the number of independent loops that you have. Remember when we defined that? And said the number of independent loops, you have to know how many nodes and how many branches and stuff like that. Or the independent loops is the number of inner loops. So you have two inner loops, you can write two KVL equations, but you're not absolutely obligated to write your KVL around the inner loops. You can decide to write one inner and one outer loop. They're still going to be independent equations. You have a question? The voltage across them is going to be the same. So V2 and V3 should be the same, right? Well, I'll tell you what, let's prove that. So why don't we write KVL across or around the second inner loop, one on the right, okay? So if you were to write that, and you're starting at the bottom left corner as I do, and you're going from here, and you're going up like that, okay? Is that a voltage rise or a voltage drop? That's a voltage rise, equal V2, okay? And then I'm going to go around, and I'm going to go like this. Is that a rise or a drop? This one. It's a drop, okay? So this rise, V2, is equal to this drop, V3, and therefore you get one more equation. The third equation, V2 equals V3. Okay? Now, you still need to use Ohm's law, and let's do that. I want somebody to give me Ohm's law for the first resistor here. Yes?
V1 equals 8 times
V1 equals 8 times I1, exactly. Okay, the current through that resistor is I1, and it is flowing inside that resistor from the plus sign to the minus sign, so it is in accordance to Ohm's law, and you can write that. Okay, now I need somebody to give me Ohm's law for this one. Yes? Exactly, V2 equals 3I2. And what about this one here, the last one? I want Ohm's law for this one. What do I have? Yes?
6 times I3.
So V3 equals 6I3. Okay? So now with all those different equations, we have one KCL relating I1 with I2 and I3, 2 KVLs, and 3 Ohm's law, Ohm's law, instances of Ohm's law. Now you're going to use all of these, you're going to perform some substitutions, you're going to solve them together, and you're going to find the currents and voltages in the circuit. Okay? So V2 equals V3, so that makes it easier. Anyway, I'll leave that to you. You can look up in the book. It's just some math now, okay? Just some substitutions. So this is the typical way you would use KCL and KVL and Ohm's law together to solve a circuit. Now look at that. This is not a large circuit, okay? It's just like one source, 3 resistors. That's not very big. That's not a very complicated circuit. And already to be able to solve that circuit, what did we do? We had to have 6 equations. Okay? So it really if you have a circuit where you have 2 or 3 sources with a few more resistors and maybe throw in that later in the term a capacitor or an inductor. You cannot keep solving all of the circuits by instances of KCL, KVL, and Ohm's law. We have to develop some methods to kind of simplify our circuits, speed up the solution, come up with tricks to reduce the number of equations that we have that we need to solve together. Okay, so that's why, like I said, that the basis of circuits is always going to be KCL, KVL, and Ohm's law, but we don't just apply these repeatedly. It becomes too difficult at some point, too many equations. So we're going to develop methods later on to kind of reduce the size of the problem, but all of those methods have to be based on KCL, KVL, and Ohm's law. Okay, this is really the basis of everything that we're doing in this course. Okay, the first thing, if you have resistors in series, you need to reduce that a little bit, and the way you do it is you find an equivalent. So if you have here a number of resistors in series, R1, R2, R3, and so forth. In this example, I have 7 resistors in series, and I'm going to replace them with one equivalent resistance. The equivalent resistance of any number of resistors connected in series is the sum of the individual resistances. Okay? So basically, you're going to say, oh, my equivalent resistance, R equivalent, is the sum of all of these. And you're going to be able to use that to your advantage. If you have a number of resistors in series, you replace them with one equivalent, the sum of all of them, and that automatically reduces the size of your problem. Okay? Now, from that, we come to the principle of voltage division. Voltage division is a very, very interesting tool. And if you understand it, you're going to spot it directly. Every time you see a circuit, say, oh, look at that. I have these resistors there. I have this voltage. I can do a voltage division. And it really works well. It's very helpful. So, when you have a circuit where you have a number of resistors in series together, and you have a certain voltage applied across the whole group together, like one voltage drop or one voltage applied across a number of resistors in series. So this is illustrated here by having R1 in series with R2, and I have this voltage source Vs, which is applied across both of them together. From that, you can find the value of V1, which is across R1, or V2, which is across R2, in a very easy way. But again, it's obviously based on KCL, KVL, and Ohm's law, so we're going to start from basic principles. KVL says, if you go around this loop, Vs is a voltage rise, V1 is a voltage drop, V2 is a voltage drop, you end up having that first equation. Vs is equal to V1 plus V2. Second equation, Ohm's law, V1 is IR1. And because those two resistors are in series, then it's the same current I, right? So we don't say I1 and I2, we just say current I. And then the second voltage V2 is equal to IR2. Now if I combine all of these together, I end up with this equation, Vs equals to IR1 plus IR2. I is common, you have Vs equals to I times R1 plus R2. And from there you can find the value of the current I. I is equal to Vs over R1 plus R2. Okay, is everybody following so far? All right. So this is how we were able to find the current I. I is equal to Vs divided by R1 plus R2. How do I use that? I'm going to go back to remember the second line, V1 equals IR1. Now I have an expression for I. I'm going to use it there. So V1 is equal to Vs over R1 plus R2 times R1, and you end up having this expression in the rectangle. It tells you that V1 is equal to Vs, which is the total voltage, multiplied by R1, which is the resistance in question. That's across which you want to find V1. Okay, so V1 is equal to Vs times R1 over the sum of the resistances. It also tells you that V1, the voltage across R1, is proportional to the value of R1. That's why you find R1 in that equation. And if you use the second substitution, you end up having V2 equals Vs times R2 over R1 plus R2. Now this is called the voltage divider rule. The voltage divider rule states that if you have a number of resistors in series, R1, R2, R3, R4, R5, and you know the total voltage across them, let's say it's Vs, you want to find the voltage across one of them, let it be R4 for example. So I'm going to find V4. V4 is equal to the total voltage Vs times R4 divided by the sum of the resistances. Okay? So it works for 2 resistors, it works for 3, it works for any number of resistors. You don't have to keep writing, KVLs and Ohm's laws and doing substitutions. You can memorize that and you can use it right away. And you have to know this rule, okay? It's a rule that you have to know. Please memorize it and use it. If you have a number of resistors in series, you want the voltage across one of them. That voltage is equal to the total voltage across the series resistors together, Vs, multiplied by the value of that resistance divided by the sum of all the resistances together. Any hope?
If we take a 3-minute break, we can swap computers and hopefully that'll bring everything back.
Yeah, so the problem is probably somewhere on my laptop, right? Okay, let's try to fix that.
Could you copy your PowerPoint onto this?
Yeah, sure. Sure.
Now, if you're just trying to get to the one. Yeah. Perfect. Sorry. Basic laws, right? Yes. It's almost certainly got it. Is it working now? Yeah. Okay. Okay. Up to.
Okay. Yeah, but I need to see myself here as well.
Oh, sorry.
So the way I do it, I don't extend. I do extend actually.
Okay.
So let's see. What is this? You pushed it.
Yeah, I moved it over to
Yeah,
the screen. I can grab it though.
Yeah. Yeah, if we just do that here. No.
sorry,
Excuse
go
me.
ahead.
Yeah, just gonna take it to the screen like that.
Ah, perfect.
Okay, so yeah, and at least I see myself. So that's
Okay, and I'll take a look at that, make sure this
Sure.
is working. But I
Thank
think
you.
That's good.
okay. I hope it's gonna work now.
Okay, you're all good.
Okay, thank you very much. All right, so thank you for your patience. We're picking up from where we left off. So this is the voltage divider rule, okay? Now we're going to apply it here. For the shown circuit, find V1 and V2, and we want to apply voltage division, the voltage divider rule right away. So I have here a 3 ohm, 2 ohm. Okay, so what does it tell me? The voltage divider rule says if I have a voltage like that, between across these two resistors in series. So it tells me now that I can automatically find this voltage and this voltage, and please notice the polarity. Okay, this plus that has to sum up to that. So this one, the first voltage, V1 equals 20 times 2 over 2 plus 3. Okay, that's 40 over 5. That's 8 volts. So in one step, I found V1. Again, how did I do that? The voltage V1 the total voltage Vs, which is 20, multiplied by the resistance that that I'm concerned with, this one, that's 2, divided by one of the two resistances, 2 plus 3. So in one step, you get V1. I understand. I know. I just put it in this way because how it should be according to the rule. Okay, I'll explain that right now. I'll tell you what I'm doing. So if you look at that, well, I'm going to call this one set of V2. Now I can apply my Vx. I'm equal to 20 times 3 plus 3 to 12 volts. Okay. Now this is the proper application of the voltage divider. Now, as your colleague just pointed out, they're asking for V2 with a reverse polarity, right? They want to know how much is this voltage if I put a plus here and a minus there, and this one is called V2. Okay. Now I found Vx like that. That's 12 volts. How much would be V2 that they're asking for? How much? Again, you have this resistor, 3 ohm. I was able to find that this polarity is 12 volts. They want me to find V2. How much is V2? Yes, it's negative 12, okay? So it's a bit confusing with the polarities, I understand. But just always keep in mind that voltage division works. I mean, keep this imprinted in your head like the way it should be. Plus, minus, plus, minus. Okay, if this is V1, this is V2, R2, and you have the total voltage, Vs. This is the template. This is the original circuit from which we derived. Applying the rule, I have to keep this in mind. Voltage V1 is Vs R1 over the sum of the resistors. Voltage V2, etc. And if you have more than 2 in series, you can do that. Now, if it happens that they're asking you for a voltage and the polarity is reversed, then you have to just remember that whatever you're solving for has to take a negative sign at the end. Okay. So that was about resistors in series. Now we're going to look at resistors in parallel. If you have resistors in parallel, look at that. We define resistors in parallel, or any elements in parallel for that matter, as being elements that are connected between the same 2 nodes. So look at that. R1, R2, R3, R4, all of these are connected across from the same 2 nodes. The top node is called A and the bottom node is called B. So we say that these are resistors in parallel. Now, if you want to replace a group of resistors in parallel by the equivalent value, R equivalent, we do it using conductances. We say that the equivalent conductance of resistors connected in parallel is the sum of their individual conductances. Okay? Now, when they're in series, you add the resistances. When they're in parallel, you add the conductances. So you have G equivalent equals the sum of the different conductances. Now, if you want to stay with resistors, you want to work with resistors, it's going to look like that. You want to work with resistances. 1 over R equivalent, 1 R1 plus 1 over R2 plus 1 over R3, etc. This is how you combine resistors in parallel. Okay? So for example, (6 ohm, 3 ohm, and 2 ohm. Okay, I want to see how that can be reduced to an equivalent resistance R equivalent. Okay, so you're going to say 1 over R equivalent equals 1 over 6 plus 1 over 3 plus 1 over 2. How much is that? It's 1 over 6 plus 2 over 6 plus 3 over 6, right? Common denominator. That's equal to 1 or 1 Siemens. So that's 1 over R equivalent. R equivalent equals 1 ohm, which is, I mean, the inverse of that. Okay. Now, this is a very simple example. This works out nicely. 1 over 6 plus 1 over 3 plus 1 over 2. That's simple. But if you have values of resistances that don't work out too nicely here, for example, if you have, you know, resistor 10 ohms, 20 ohms, and 25 ohms. Okay. Now you're going to find that using that gets a little bit more complicated. 1 over 10 plus 1 over 20 plus 1 over 25 equals, and so forth. Yes. You can use, yeah, of course. Yeah, fractions, decimals, whatever you need. But you're going to discover that often you don't have a lot of resistors in parallel. You have, usually, you want to apply this equivalency or like find equivalent resistance with 2 in parallel. With 2, it becomes a lot easier. And that's kind of a special case, because look at that. If you have these 2 resistors, R1 and R2 in parallel, and we use the law, the rule 1 over R equivalent equals 1 over R1 plus 1 over R2, then I can kind of mathematically say that. That's equal to, look, I'm taking R1, R2 as a common denominator, and I get R1 plus R2 over R1, R2, right? It's just math. I'm adding fractions. So this is 1 over R equivalent, so I'm going to take the inverse of that to find R equivalent. That's equal to R1, R2 over R1 plus R2, the product of the resistors divided by the sum of the resistors. Now, this is very helpful when you have two resistors in parallel. You want to find R equivalent, and I'm going to apply it here. Okay, let's take 6 and 3, 6 ohm and 3 ohm. Tells me R equivalent equals product over sum, sorry. 6 times 3 over 6 plus 3. Okay, so how much is that? Okay, so yes.
If you had, say, 8 resistors in parallel, would you be able to use that sort of 4 times?
If you have any number of resistors in parallel, you can take any two resistors and apply this rule for any two resistors, and you can do it kind of successively. Okay. So actually, for example, for this one, I found that if I take 6 and 3 in parallel, I end up having 2 ohm, right? And now I have 2 ohm in parallel with 2 ohm, so I can do it again. 2 in parallel with 2, it's product over sum. That's 4 over 4. That's 1 ohm, which is what we. So you can do it successively with every two resistors in parallel. Yes, you can do that absolutely, and that's typical. That's very often the way. So the equivalent resistance of two parallel resistors is equal to the product of the resistances divided by their sum, and this is also like kind of a trick. It saves a lot of time. If you know that two resistors in parallel, you want to reduce them to find an equivalent resistance, it's product over sum. But beware, it only works every 2 at a time. You cannot take like 3 or 4 or 5 resistors and say, oh, product over sum. So you just multiply the values and you divide by the sum. It doesn't work it works only with 2. So example, find R equivalent for the circuit shown. You have this network of resistors, 4 ohm, 1 ohm, 2 ohm, 6 ohm, 3 ohm, 5 ohm here, and 8 ohm there. Now we want to find the equivalent resistance that I see from here, which means I want to reduce all of that between those same two terminals. I want to know how much that would be. Okay. So all of this network has to be kind of equivalent to that. Now, my question is, we're going to take it resistors in parallel. Yes. 6 and 3. Do you see that? This here is one node, and this here is another node. So 6 and 3 are indeed in parallel. And I can say 6 parallel with 3. Do you see that notation? These two slanted lines means in parallel. 6 parallel already did that. Product over sum, 6 times 3 is 18, divided by 6 plus 3, divided by 9. That's 2 ohm. Okay, so you end up having, I'm going to do it, in many steps. This is my 2 ohm now, right? And 2 ohm here, 1 ohm, 4 ohm, 8, and 5 ohm. So I replaced this parallel combination with this element here. Okay. What do I see now? Can anybody find two resistors in series? Two resistors in series. Yes. 2 ohm and 2 ohm. Okay. And what do we do when we have resistors in series? We sum them up. So these two together give me 4 ohm, right? I see two more in series. Can anybody see that? Yes. See that? They're also in series. Okay, so this is 6 ohm. So now I have a network that looks like this. 6 ohm here, 4 ohm here, 4 ohm, 8 ohm. So what do you see now? Yes. The 4 ohm and the 6 ohm are in parallel now. Okay, so I do 4 parallel with 6. That's product over sum, right? 4 times 6 over 4 plus 6. That's 24 over 10. That's 2.4 ohm. Okay? And this is how it's going to look like now. Eight ohm, 4 ohm, 2.4 ohm. Now, I have 3 resistors in series. In series, I don't have this restriction of taking every 2 at a time. You can just add them all together. Okay, 3 resistors in series, that's 4. So that's the final answer. R equivalent is 4 plus 2.4 plus 8. Okay, that's 14.4 ohm. All right, so this is how you do resistors in series. Now, what do we have after that? Yeah, we still have. Okay. All right, so we're stopping here. Thank you very much. I have a simple announcement, and I said that on course link, especially for those who are not in the class here. Lab 0 is essential for those who took the labs before. If somebody is doing that course for the second time, then I am giving you an exemption from lab 0. You can come to lab 1 directly, but for everybody else, you have to do lab 0. If anybody cannot come to lab 0, you will not be allowed into the lab for the subsequent weeks. And for that, I'm making provision at the end of the term for anybody who's away on work terms. They can come, or you can come and do all of the labs at the very end. We're going to repeat lab 0, and then you can go into lab 1, 2, 3 at the end. Thank you very much.